Okay, here we are to talk about the exception cases in section 6.1. So our first case to discuss is our independent inconsistent system. Independent meaning that we have different equations, inconsistent meaning that there's going to be no solution. So first of all, I'm going to put each equation into slope-intercept form. So the top equation, just moving the x, I get y is equal to negative 2x plus 3. And then the second equation, moving the constant over to the right side, I get negative 2y is equal to a 4x plus, minus 2. And then dividing everything by this negative here, here, and here, we get that y is equal to a negative 2x and then plus 1. And what we should notice here is that we have the exact same slope. When we have the exact same slope and different y-intercepts, we have equations of lines that are parallel. So we have parallel lines here. And when we have parallel lines, those lines are never going to touch, never going to cross. And so by just investigating those things, we could see that there was no solution, because we would know that parallel lines will never cross and never touch. Now let's look at that visually. So again, I had to graph this. Now you see, here's my graphs of each of those two lines, and we see that they're never going to touch, never going to cross. However, you kind of notice that this one looks like it's trending in toward this one. Well, that's just my graphing, my line wibble-wobbled, and I told you about wibble-wobble of lines before, that we're only human and we're never going to get them perfect. So graphing is really not a good method to see if we have no solution or not, because it always kind of makes up or leads us to the question of, well, is it accurately drawn enough? Are we actually going to touch at some point? And that's why we come back to seeing through slope-intercept form parallel lines telling us exactly that we have no solution. Now let's move on to our next example here, our example where we have the next type of system, which are dependent consistent systems. Dependent meaning we have the same equation, and consistent meaning that it has a solution. So again, the first thing that I'm going to do is I'm going to put these in slope-intercept form. So y is equal to negative 3x. And then dividing each thing by 2 here, we see that y equals negative 3x. And what you see is that we have the exact same equation. And when we have the exact same equation, well, obviously, everything that solves this one is going to also solve this one. And so the solution set are what we're going to call infinite solutions. Now, at some point in time, what we learn to do is we learn to just write the solution set as an equation that describes these things. But I'm just going to allow us for this time being to say infinite solutions and leave it at that. So now let's go ahead and show that on the graph. So here's my graph right here, and you see I've just graphed the one line because these two lines are exactly the same, and there's my solution. It's everything that solves one solves the other. And so I say infinite solutions this time around because there is no way of just saying real numbers, because it's all real numbers in x and all real numbers in y, but they have to be paired in this special way to show the solutions. So a graph is nice of this because it shows exactly what we are talking about. All right, now moving on to our last special type of system. This special type doesn't give me anything but a consistent solution, but when you see these two lines graphed here, you see the problem is that those things intersect right there. I have no way of knowing what that is. I mean, I could guess about it. I could say, okay, well, x looks to be about 2/3 and y looks to be about, oh, I don't know, 2/5 maybe, negative 2/5, but I don't know for sure. And there's no guessing about these things. So example 5, you see, is not really well solved by using this graphing method because it's inexact. And that's what leads us to our next type of solutions, our substitution method and our elimination method. But before we head there, we'll look at how we solve systems using tables of values. And this will again call back to 4.3. See you in the next video.